Hello students, this is a brief tutorial that will lead us through the instruction we need to create shorthand electron configurations. We'll of course need to reference a periodic table. I'm going to set this to the side as I show us this blank periodic table. As we see, it mimics the true periodic table. However, it is vacant of element symbols, atomic number, etc. What we do to show us kind of, the hints to this is go one by one, and we'll start to skip around, but to create and leave the very end of the electron configuration of each element in the element block. All right, let's dig in. Hydrogen, of course, has one electron, so therefore, it is in the 1s1. Then we go to helium, which is 1s2. All right, now we're on to lithium that has 3 electrons. Well, 2 of them are going to go in the 1s2, and the third will go into the 2s1. Then, of course, we move on to beryllium that has 4 electrons. So, first 2 will go into the 1s1, and then the 2s2. Then we proceed to boron. Boron has, of course, 5. 2 in the 1s2, 2 in the 2s2, and then 2p1. We then go to carbon with 6 total electrons. 1s2, 2s2, we have 2 in the 2p2. Do you see the trend? I'm sure you could go ahead and fill in 2p3, 2p4, 2p5, 2p6, and I'm sure that you could predict what would be underneath lithium, of course, for sodium, which has a total of 11 electrons, 1s2, 2s2, 2p6, 3s1. 3s2, then 3p1, 3p2, 3p3, and so on and so on. All right, ladies and gentlemen, have you ever wondered why the periodic table is so chunky? Why do we have these 2 columns that stick up, then we have this lower region, then this region that sticks up, and then these 2 rows down here? Well, if we continue to fill, I bet you could easily fill this in as 4s1, 5s1, 6s1, 7s1. Horizontal rows are periods. In the first period, we are putting electrons in the first energy level for these elements. In the second period, electrons are placed in the second energy level on the very outmost of the atom. Then we're going to find our outermost electrons in the third energy level for the elements that are found in the third period, and then 4 and 5 and 6 and 7. I'm sure that you could fill this in as well. Actually, the elements, that's 7s2, the elements that are found in these first 2 columns, we block them and call this the S block, because these elements have their highest energy electrons last placed in the S. Now, of course, helium, put over here because it has a full first energy level, so it will behave like noble gases. Hence why it's over here, but really, it should complete the S block. Check this out. We know the P sublevel holds 6 electrons. So that's why there are 1, 2, 3, 4, 5, 6 columns in what we would call the P block. This entire area, the P block. And the energy level where we're putting these electrons correlates to the period number. So second period, the 2p sublevel. Third period, the 3p. Fourth period, 4p. Then 5p, then 6p, then 7p. Well, let's continue. We know energetically that S is of lowest energy as far as sublevels are concerned, then P, then D. D holds 10. So look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, amazing, amazing, amazing. So this whole area is called the D block. All right, what are we missing? The F. And F, of course, can hold 14. So you know what's coming. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, we'll talk about what's going on while we have extra. But in general, this, of course, would be our F block. Making more sense of the periodic table. All right. Shorthand method then. So, ladies and gentlemen, if you were asked to create the electron configuration of sulfur. All right. Let's get the electron configuration of neon. Neon has 10 total electrons. And so we would create 1s2, 2s2, 2p6. Well, why don't we proceed onward and move to the 11 electron-filled sodium. Sodium is 1s2, 2s2, 2p6, 3s1. Magnesium, 1s2, 2s2, 2p6, 3s2. And then eventually, sulfur, 1s2, 2s2, 2p6, 3s2, 3p4. All right, we talked about the most important electrons that we use to predict reactivity are the valence. Those electrons found in the highest energy level. So for sodium, it's the 3s. For magnesium, the 3s. For sulfur, the 3s and the 3p. The highest energy level. These are inner core. They will not be involved in any kind of chemical reaction. It's not that they're disregarded, of course. They give some personality to our different elements as far as reactivity. However, whenever we're looking at electron configuration, these are what we want to know. Do we see sodium, magnesium, and sulfur, which are found in the third period, in the S and then the P block? Their inner core electrons are the configuration of the noble gas before the third period, the noble gas in the second period. So, the way that we can do shorthand notation is begin with the element, put the noble gas in the period above it in brackets. And what that means is all of the electrons that neon brings. So writing neon in brackets is saying the 1s, the 2s, and the 2p. Now we begin to add on to get to our elements. All right, so sodium, starting with neon and all the inner core electrons for sodium. All right, sodium is in the first position of the S block, the first position. So we know the electron configuration it will end with is S1. But of course, we need to identify what S. Well, sodium is 1, 2, 3 periods down, so we give it a 3S1. So you don't have to create this entire cataloging. We can say, okay, noble gas before it, brackets. It's in the first position of the S block, S1. It's the third period, 3. That's the shorthand notation. You can do the same for electron orbital diagram. Neon in brackets, it's in the first position of the S, We know S only has one orbital. We're going to label that to be 3s because it's the third period down. We know it's 1 over. It's just going to have one arrow to show that one electron, either pointing up or pointing down. So we can do for orbital notation as well. For magnesium, it's here. So the noble gas before magnesium is neon. Putting neon in brackets. Magnesium is the second over in the S block. So we know it's going to have an exponent of 2. 1, 2, 3, third period down, and we're done. Orbital notation, we're good. So how about for sulfur? Sulfur, the noble gas before it is neon. Then, we've accounted for all the electrons of neon. Now we're starting here, and we need to build to get ourselves to sulfur. Well, first, to get here, we need to go through the S block. We need both of them. So, that will be S2. And which S? 1, 2, 3, third period down. Now we move to the P block. Which P? 1, 2, 3, third period down. And sulfur is 1, 2, 3, 4 columns over. Electron configuration for sulfur. Orbital notation, we know 1 dash filled, and then 4. You're going to have 2 lone, a pair, and these just have to have the same spin. Orbital notation for sulfur as well. All right. Well, what if we have something to do further down, beyond the third period, where we start to involve D and F? Well, if we go back to our off-law charts, 1s, then 2s, then 2p, then 3s, then 3p, then 4s. But where do we go after 4s? 3d. So, energetically, the electrons in the 4s must spend more of their time closer to the nucleus. So we put electrons there first. Then we return to the 3d. 3d1, 3d2, and on until 3d10. Then we go to the 4p. After the 4p, where do we go? 5s. Then to the 4d. And so on and so on and so on. So what if you were asked to get the electron configuration for, let's just do iron. All right. Iron is number 26. That is here. Zinc. Let's see. Copper, nickel, cobalt, like zinc, copper, nickel, cobalt, iron. Yeah. Okay. So the noble gas before iron, 1 period up, is argon. To get to iron, we need to go through the 4s first. Then the D block is the period number -1 as far as the energy level. So fourth period, 1, 2, 3, 4, 4 minus 1, that's how we get 3D. And then iron is 1, 2, 3, 4, 5 over. No! 1, 2, 3, 4, 5, 6. I have the wrong block, for crying out loud. There we go. So it would be 3D6. Yes. And we could do orbital notation. And put them by themselves first. And then double up. All right. Well, it gets a little tricky whenever we get to the F block. So, again, if we go to our off-law charts, okay, when do we start seeing F? We start seeing F after 7S. Well, I'm sorry, after 6S. After 6S, that's where after 6s, yeah, that's where 4f. So in the 6th period, the 4f comes after 6s. So to know the energy level that we're going to place f electrons in, it is the period -2. The 6th period has 4f. Then after 4f, we go to 5d. 4, 5. Okay, so if you remember, 6s, then we fill the 4f, then come back up to 6d. Excuse me, 5d. 6s, then 4f, then 5d. Yeah, then 6p. Whew. All right, then after 7s, it's 5f. So, why don't we dig in and just conquer a really, really large one? Let's do tin. All right, so tin, ladies and gentlemen, is the 5th period, 1, 2, 3, 4, 5, and it is 2 positions over. Tin isn't so bad. Let's do lead. Let's just jump in a little deeper. Let's do lead. Okay, so lead, the noble gas before it is xenon. All right, so xenon. Now we start here and work our way all the way over. So, all the electrons xenon brings. Then, 6s2. We can't forget that then we go to the 4f. Okay, to work our way all the way over there, we need to go through the 6s. We need to go through all of the 4f. Then we come back up to the 5d. We need all of them. Then we enter the 6p and give us our 2 electrons. Now, does shorthand notation address most of the questions we have? Can we diagnose how many valence electrons lead has? Absolutely. 4. Can we create the Lewis dot for the lead element? Absolutely. Can we, from orbital notation, determine how many paired, how many unpaired? Absolutely. So the shorthand method is a sound way to represent the electron configuration of electrons or elements that have a ton of electrons. So it just saves us some work, but it also gives an understanding to why the periodic table is as it is. So the S block, the P block, the D, and the F, those are going to be the highest energy electrons for those elements that are found there. Now recall, D and F, those aren't going to give us valence electrons, but they could be the highest energy, not the highest energy level, but the highest energy electrons. So we just want to make sure we understand our terminology. Best of luck, students.